Welcome to Chemistry at Heininga High School. I'm Brian Brown, and today we're going to be looking at our second set of notes from Chapter 13, our States of Matter chapter. And what we're going to be looking at today is transitioning from gases to solids and liquids, and then looking more in depth, at least the liquid state today. So one of the fundamental things that separates gases from solids and liquids is the fact that solids and liquids don't have attractive forces. So the types of forces we talked about earlier are called intermolecular forces. When we have a gas particle, remember, part of kinetic molecular theory said we assume that there is no attractive force and repulsive force between individual gaseous particles. And that's because of the distance that separates them and the speed at which those particles move. Well, that's not true in our solid and liquid form. They have definite attractive forces, and those attractive forces are very, very relevant to their behavior. Now remember, fundamentally, there's two different types of attractive forces. One would be intramolecular forces, and those are the forces that hold a compound together. The ionic compound, how are the ions held together? The covalent compound, that would be the bonds between the nonmetal molecules inside. And then finally, metallic bonding. When we have metallic substances, the bonds that hold those together. Well, that's really not what we're looking at in this chapter, because what we're looking at is not the forces inside holding compounds together. We're looking at the forces in between, which are our intermolecular forces. And those are the relevant forces that we talked about earlier in the year, because those are going to cause the attractions between liquid particles to each other and liquid particles and other types of particles and solid particles to each other. And those would be the London forces, the dipole-dipole attractions, and the hydrogen bonding forces that we looked at earlier for molecular substances. And in the case of breaking an ionic compound, if we're going to melt it, we have to actually break the ionic bonding that is within it. And that is actually an intramolecular force. And if we're talking about melting a metallic substance, well, the bonds between the metal atoms inside there is actually explained by metallic bonding. But when we're dealing with molecular substances, we're just looking at the intermolecular forces, the true forces of attraction between molecules. Now, in the case of a solid and a liquid and a gas, what fundamentally separates the different states from each other is at a particular temperature and pressure, two different antagonistic forces are competing against each other. One would be the kinetic energy of the particles, the literal energy of the movements of those particles, which can help particles break away and move against each other, versus the strength of those attractions between the particles, the intra and intermolecular forces, depending on the situation. And like I said, most of the time we're looking at molecular substances, so typically we're going to talk about intermolecular forces related to this. Well, those are competing forces. Intermolecular forces attempt to hold together. Kinetic energy would give you the energy to break apart. So really, which state we're in, solid, liquid, or gas, depends upon who's winning this battle of attractions versus the energies of motions involved. When the particles are moving slow enough, the kinetic energies aren't enough to overcome the attractive forces, and you have a solid. If you have a little bit more kinetic energy, you can start to break away, but you're only partially breaking away and you have your liquid. So the kinetic energy has started to overcome the attractive forces. Well, when you go to a gaseous substance, you've completely overcome those attractive forces and the particles break away. So really the difference between which state at a given temperature and pressure is related to who is winning, the kinetic energy or the attractive forces in between. Now, in the case of a liquid, things are a little bit different than they are in a gas because gases have no attractive forces and liquids definitely do, and they have a huge effect on your behavior. Your molecules are relatively close together in a liquid, but not so tightly packed that they can't move around. And that's really what's separating them from a gas and a solid. So they don't have a fixed shape. They're going to take the shape of the container because they are free to move around. And unlike gases, liquids are held together by attractive forces. Now, kinetic energy has partially overcome those attractive forces, but they're still relevant and they exist, and that holds liquids clumped together. But remember, the liquid particles themselves are free to move and flow. They're just restricted in that movement because of the attractions of all of the liquids around them. So we have attractive forces for the very first time, and that has a big impact on our behavior. We can't go anywhere inside the container. We're going to stay clumped together in the bottom of the container, taking the shape of the container. And this is going to give liquids a fixed volume. So while we don't have a fixed shape, we take the shape of the container because we can flow, we do have a fixed volume. The particles have a relative set distance between each other. And overall, the liquid is then going to have a measurable volume because we've got a bunch of liquid particles together, unlike the gas particles, which are independently moving around. Now, if we could look at liquids on a particle level, I know on the tape here it's going to come out a little bit odd looking, but fundamentally we have particles that are significantly closer together than what we saw in the gaseous state. And the particles are also moving slower. And the reason they're clumped like this is the gas or the liquid particles, unlike the gas particles, are actually holding on to each other. They have intermolecular forces that keep them clumped together, but they're not holding so strongly because of their speed and once again the distance. They're not so strongly held together that they can't move anywhere. Now, other properties of liquids. Well, our molecules are not moving fast enough to break the attractive force. So kinetic energy, while it's strong enough to partially overcome attractive forces, it's not like a gas particle where you can go anywhere. Those attractive forces are still relevant, and we haven't broken them because we just don't have enough energy. So what really happens is liquid particles freely move around, but they don't leave each other. When you get to the surface of the liquid, the surrounding liquid molecules hold you in. And liquids themselves are not very compressible. They're packed fairly close together, as you saw in that last picture. So unlike gases, which are so far apart they can be easily compressed under the right conditions, liquids are considered, just like solids are considered, to be incompressible. And that's a very useful feature in brake lines because if you exert a pressure on one side of the liquid in the brake line, that same pressure will get exerted on the far side. If you have an air bubble inside there because air is compressible as a gas, that would actually contract and your force wouldn't be transmitted throughout. And therefore your brakes wouldn't function. Now, we talked about densities in gases because the gas particles, excuse me, I knocked my headset, sorry for that. Because we talked about density with gases, I want to make sure we relate the idea to liquids as well. Now, we said gases had a very low density because they were spaced far apart and relatively low mass. Well, when we look at the density of liquids, remember our intermolecular forces are holding our liquids together. That's putting them in a smaller volume than the entire container. And remember, density is mass over volume. Well, if the number on bottom is smaller, that means the density is going to be higher. So fundamentally, liquids are significantly more dense than gases are. Fluidity, one of the things we talked about with gases is their constant random rapid straight line motion. Well, liquids are moving relatively rapid as well. And while there are attractive forces holding them together, it doesn't prevent them from completely flowing. Now, liquids aren't as fluid as gases, but it is true that the molecules aren't so close together that they can't move. The intermolecular forces make them less fluid than gases, but they are still fluid. They are able to move. So gases are actually the perfect fluid. Liquids are restricted in their flowing. And the stronger the intermolecular forces, the harder it is going to be for a liquid to flow. Picture something like maple syrup. Maple syrup is a liquid too, but it's a very thick, and we call that viscous liquid, and that's because the intermolecular forces are holding together. And viscosity then is a way we have of measuring the flow of different substances. And liquids are more viscous than gases are because they have intermolecular forces that gases don't have. But all liquids aren't the same. And at different temperatures, all intermolecular forces aren't the same. So when we look at viscosity, we're looking at a resistance to a flow of a liquid. And one thing about viscosity is it's going to decrease with an increase in temperature. Remember, attractive forces are overcome by kinetic energy. So as the temperature of the liquid starts to rise and the kinetic energy starts to increase, the liquid particles move around a little bit more. They actually expand and they're more free to flow. And therefore, when you get maple syrup hot, it flows much more easily than the maple syrup when it's cold. And that's because as the temperature increases, you've got more kinetic energy and you start to more overcome those attractive forces. Now, another property of a liquid besides viscosity and density and would be surface tension. Surface tension is basically the property that allows certain types of bugs to walk on the top of water in a pond. And what you're seeing is a picture of one of those insects. Now, this is actually a water strider. A lot of people mistake it for water spider, which the name just happens to be similar, but it's not a water spider because this is not an arachnid. This is actually a water strider because it literally walks on the top of water. Now, surface tension is measured as the energy needed to increase the surface area of a liquid. If I'm slowly pushing my hand down through the top of a liquid, I'm actually increasing the surface area of the liquid as the liquid starts to coat my hand. I'm creating a surface that wasn't there before. Well, different liquids have different amounts of energy to do that to increase their surface area. And what really causes this surface tension is there's an imbalance of intermolecular forces within the liquid. When I have a liquid with my particles and I'm in the middle of the liquid, remember I have attractive forces all around me. All of the substances nearby and their intermolecular forces are holding me together. But when you look at the liquid particles on the surface, that's a different situation than the liquid particles inside. We only have downward pulling forces on those surface liquid molecules, and that downward pulling force that exists between and underneath all these molecules, attracting it around, actually creates a imbalance of force on the surface, or a skin that we have to overcome to break that surface of the liquid. And if you've ever had a belly flop when you jumped into the water, you know exactly what I'm talking about. Normally when you hit the water, you have a very low surface area because of how you're diving in. That means you create a great pressure, and it's easy to push the water molecules apart. Well, when you increase the area a lot, then it gets a much lower pressure, and it's much harder to push those water molecules apart, and it can really hurt when you slam into the water when that happens. I guarantee you're going to break the surface and go in, but it's going to end up hurting as the water pushes back on you before you break in. Now, if you could change the surface tension of the water, that would lower the surface tension. So if you were decreasing the intermolecular forces, like by heating something up, and it would be easier to break through the surface of a liquid. And not only do insects do this, but there's a type of basilisk known as the Jesus lizard, because literally it escapes predators because it's very light and small, and it has very large web feet. Now, if it stood in place, it would basically fall through the water, but it's able to push off of the surface tension of the water and very quickly kind of skate across the surface to escape from prey. The large animal running behind it would actually get captured. And another thing the surface tension of water creates is the fact that water molecules, when they band together in a drop or a bead, they don't go completely flat. That surface tension basically has to be broken in order for this molecule to flatten out. And water molecules have relatively strong hydrogen bonding, which means they're going to bead up on a surface that's not attracted to them. So when you drop a liquid into the air, it ends up forming a nice sphere because that would give it basically a balance of those forces around and inside the particle. So that's why when you drop a liquid into the air, it forms a spherical shape. It deals with the surface tension, the intermolecular forces. Another consequence of intermolecular forces that affect properties of liquids is something known as capillary action, or wicking. And this is basically why shirts get wet. When you put them near water, the water actually gets absorbed up into the shirt and into sponges. That's by capillary action. Now, you have fundamentally two different types of intermolecular forces at work here. Cohesion is the force of attraction between identical molecules. So water molecules sticking to water molecules, that's a cohesive intermolecular force. Well, there's a different force of attraction between water molecules and another substance. And it can be stronger and it can be weaker depending on what the other substance is. So we basically have two competing different types of attractions. Water molecules or liquid molecules holding onto each other, and then them holding onto something else. Like when you put water into a thin plastic or glass tube, not only do the water molecules stick to each other, but they also are attracted to the glass or the plastic. Now, when the adhesive force between the water and the glass is stronger than the cohesive force between the water molecules themselves, the liquid literally creeps up the side of the tube. Now, gravity is pulling them down, so it can't creep forever, but it will create a meniscus inside a graduated cylinder that we've talked about earlier in the year. So if it's a smaller glass tube, but still fairly large like a graduated cylinder, you're going to actually see that creep in the fact that the sides of the container have water molecules climbing up them just to a small degree. Now, the stronger that cohesive force would be, the or I should say, the stronger that adhesive force would be, the higher they would climb up the side of that container. Well, remember, gravity is what's pulling them down. So if we have a thinner and thinner and thinner diameter tube, we actually get what's called capillary action, which is a special type of meniscus where literally the liquid is creeping up the tube. Now remember, gravity is attempting to pull it down, but in a thin enough tube, there's enough capillary action to get the liquid to actually rise up inside that tube. And that's basically what happens with cloth. Cloth has a bunch of narrow little capillary spaces within them. And when water gets next to them, capillary action wicks that or pulls that water into the cloth, and pretty soon the whole shirt is wet. Now, if you take a bath and you accidentally lay your towel halfway in the bath and halfway out of the bath, you'll actually see this at work as you create a huge mess on the bathroom floor. Because what will happen is the liquid will literally wick up one side of the shirt and then end up wicking down the other side of the shirt, and gravity now is helping it, and it literally dumps out the entire bathroom over time onto the floor. And that is our final property of liquids.